believe it was sometime during the 1600s when ships were traveling back and forth. They had a real problem with the compasses they were using because if the ship would rock back and forth, the compass would obviously rock with it, and that motion would cause all sorts of problems for the captains trying to navigate these ships. That problem was approached by Robert Hooke, who was like the rock star of his day. This was like the man that Isaac Newton looked up to when he was younger. He was a little bit older than Newton, so he was kind of like a role model, so to say. And he approached this problem by first thinking about the concept of springs or things that have very elastic properties, meaning elasticity, meaning they will snap back to their original shape once they become deformed. So, in order to try and look at this problem, he took some springs, hung some masses from them, and he measured the displacement. So when this mass was hung on the spring, he measured how far it was displaced, and he tried to determine is there a relationship, or was there a relationship, between the force that was pulling this mass down, which was the force that was pulling on the spring, and the resulting displacement. And he did that the same way that you guys have done in class, hung some masses from a variety of different springs, measured all sorts of displacements, and generated a graph that looked fairly similar to the one you likely wound up with and the one you see here. By plotting the force versus the displacement of the spring, he was able to determine that his trend line, or the line of best fit for all the data points that he found, tended to result in a constant slope. There was a linear or direct relationship between the force acting on a spring and the displacement of that spring. He therefore determined that slope that's constant must be what's known as a spring constant. It is some constant property of that spring. K is what we use to denote that spring constant, and because K is technically the slope, which is the change in y over the change in x, the units of that spring constant would be the units for y over the units for x, which as you can see here are newtons per meter. So you can see from this graph that the spring constant, that K value, really just tells you how much force you get per meter that this spring is stretched. So if I stretch this spring 1 meter, I will get X number of newtons of force. If I stretch it 2 meters, I'll get twice that, and so on and so forth. That's where that linear relationship comes from. So this was pretty important. But it also led to the question, well, what does K indicate? What does this K value, this spring constant, what does it actually mean? And in order to understand that, I've made up a few slopes here, a few different sets of data that Robert Hooke might have come across. You can see there's one in red with a fairly shallow slope, one with a moderate slope in purple, and one in green with a very high slope. And we know that the slope is constant, which is this spring constant. So let's take a look at these three and see what that slope, that K value, actually indicates. As you can see by the red data set, there's a fairly large displacement, and that's the result of a fairly small force. The force is only somewhere around here, so a small force produced a very large displacement. If you think about that, it's kind of like a slinky. You don't really need to pull very hard on a slinky. Actually, if you just hold one end of it, gravity will pretty much pull the other end down. If we look at this purple data set here, it's a fairly moderate amount of displacement, but it also required a fairly moderate amount of force. This green data set did not experience very much displacement, but has an incredible amount of force acting on it. So if you start to take a look at this and think about it, if a small amount of force gives me a very large displacement, that's probably not a very strong spring. I didn't have to pull very hard and it stretched very far. So a small amount of force gave me a large displacement. In the case of this middle data set, I got a lot of displacement, but I also had to apply a fairly large force, so that spring is likely a little bit stronger, so to say. It took a little bit more force to get somewhere around the same displacement. And this green line, as you can see here, I had to apply a tremendous amount of force, and I really didn't get that much displacement. The spring did not stretch that much, despite the high forces that I placed on it. That would tell you that this is a very, very strong spring, and very high forces are not going to stretch this spring very far. So hopefully you can tell from looking at these three sets of data that the spring constant K, it pretty much indicates the stiffness of the spring. So a very high K value is going to be a very strong spring that's going to be very hard to deform. That would be like maybe the shocks in a car, maybe the springs on the shock system in maybe an airplane or something very heavy. And a low K value, a very low number for K, is going to be a very weak spring. Because a low K value means a low slope. So a low slope means a lot of displacement for small forces. A very high K value, again, K is the slope, a very high K value would be like this green bar, or this green line. A small displacement is the result of a large force. So it gives you a general indication of whether you're dealing with a very strong, stiff spring or a very weak, soft spring. So a weaker soft spring would be something like a slinky, and a much stronger spring would be like an industrial spring used in a machine, something along those lines. So how did Robert Hooke use all of this to actually determine what became ultimately known as Hooke's law and allows us to analyze these spring systems and elastic objects very in depth? Well, he took a look at what he had. He took a look at his data set and realized that, well, the y is really measuring the force, and the x is really measuring the displacement. He also realized that that was a straight line, so he could use the slope-intercept form. Y equals mx plus b, where y is the y-coordinate, x is the x-coordinate, m is the slope, and b is the y-intercept. So all he did was replace these variables with what his data was actually suggesting. The y is the force, so he replaced the y with force. The slope, as we mentioned, is this concept of the spring constant, or the k value, so the slope is just k. X in this case happens to actually be delta x, the displacement, so x was replaced with delta x. And b, the y-intercept. Well, he took a step back and he thought about it and said, well, when I don't apply any force to this spring, how far does it stretch? And he realized, well, no force will not stretch the spring, so really the y-intercept is 0. So through looking at all his data, he found that this relationship exists for every elastic object, for every spring, and it became known as Hooke's law. And it very simply states that the force in a spring or some kind of elastic object will be equal to that k value, the indicator of the strength or the stiffness of that spring, times the displacement caused by that force. And you can see that these variables are listed here. Now, I'd like to show a few examples just as to how this can be utilized. Here we have a mass that's being pulled by a force of 30 newtons. Some displacement has resulted, and if the spring constant of the spring is 80 newtons per meter, how far will the spring stretch? So if I list my knowns, I know the force is 30, I know my k value is 80 newtons per meter, and my displacement is unknown. But using Hooke's law, we know that the force is equal to the k value times that displacement, so 30 must equal 80 times that displacement, and I can therefore find that this spring will stretch about 37.5 centimeters or 0.375 meters. Second example, you have a mass hanging from a spring, much like in your labs, and if the spring stretches 9 centimeters when the mass is hung, what must the spring constant k be? Well, the force in this case, it's not an applied force, it's the force of gravity pulling down on the mass. So the force is going to be the 500 grams converted to kilograms, 0.500, times the acceleration due to gravity, and you'll find that that spring is being pulled by a force, a downward force of 4.905 newtons. We're given that the displacement of the spring is 9 centimeters or 0.09 meters. And when I plug everything into Hooke's law, the only unknown is the k value, and I can therefore determine that this spring must have a k value of 54.5 newtons per meter. As long as I don't change this spring, I don't overstretch it to the point where I ruin it, and I get those little, if you see a spring, it kind of has stretched sections. As long as I don't damage the spring or change the spring, I will always have this k value. That's a constant for that spring.